Hi, Theorem class. Sorry I can't be there today, so I'm making a video so we can do the lesson plan in video form. Sorry about that, but we'll give it a shot and do our best. Feel free to pause it and, back up if you need to. This first problem from the lesson plan, I'd like for you guys to try on your own because it's review from what we did last class. So I would love for you guys to pause it, work together, and try this whole problem on your own. And then when you're ready, watch the video and see how you did. Okay, so if you're ready and you've tried it yourself, in this problem, we have to find g of 3, g prime of 0, and g double prime of 2. But first we need to make sense of this situation up here using the fundamental theorem of calculus. And with the fundamental theorem of calculus, basically the idea is if we take the derivative of an integral, those operations cancel each other out. So I'm going to take the derivative of this expression or equation, and I get g prime of x equals, and then I cancel the integral and just take x and plug it in for t, and I get f of x. And we are told that the graph below is f. And so now we've identified that it's not only f, it's also g prime of x. And since all our questions are about g, we're going to think of this graph as a first derivative graph. So for g of 3, we're going to use the given integral because g is before we took the derivative. So it's the integral from 0 to x, which is in this case 3, of f of t dt. And that's going to be the area between the graph and the x-axis. So from 0 to 3. So from 0 to 3, this chunk right here, we're finding this area. And to do that, we're going to break this figure up into some familiar geometric shapes. I've got, it looks like 1/4 of a circle, a little rectangle, and a little triangle. The rectangle is 2 units. The triangle is half of a unit. And then for that part of the circle, well, the area of a circle is pi r squared. But since this is 1/4 of a circle, I'm going to do pi r squared divided by 4. So the radius of this circle is 2. So I'm going to do pi times 2 squared and divide it by 4 because that little chunk is only 1/4 of a circle. And that gives me 4 pi over 4, or just pi. So back to this integral, which represents that area, it's going to be 2 plus 1/2 plus pi, or we could say 2.5 plus pi, or if we wanted to do it with common denominators, 5 over 2 plus pi would work as well. Okay. Then for the next part, g prime of 0, remember this was area, this is going to be the y-coordinate on the graph because this isn't a g prime graph that we're looking at. So we're just finding the y-coordinate on the graph when x equals 0. And that is this point up here at the top. The y-coordinate is 3. And lastly, for g double prime of 2, this is going to be the slope of the tangent line, because if this graph is g prime, g double prime is its derivative. So we need the derivative of this graph at 2. Now, at 2, we have a curve going into a straight line making a sharp corner, and that point is not differentiable. So we can't find the slope of the line at 2 because the derivative doesn't exist there. So we say does not exist. In this next part, we are determining where g of x has relative maxes and relative mins. Now remember that g prime of x equals f of x, so we're looking at a g prime graph or a first derivative graph, and relative maxes and mins occur when g prime equals 0, so I'm looking at these x-intercepts. And G would have a relative max when G prime goes from positive to negative, because that's where G would increase, then decrease, making a max. And G will have a relative min when G prime goes from negative to positive, because that's where G would decrease, then increase, making a relative min. So the x-coordinate, where g of x has a relative max, is going to be when x equals 3, and g of x has a relative min when x equals 5. And your justification is exactly what g prime is doing, that g prime goes from positive to negative or negative to positive. And in these last two parts, well, in part D, we're looking for points of inflection on the graph of G. And if this is a G prime graph, G double prime is its derivative. So we're looking for where the derivative of this graph equals 0 and changes sign. Basically, we're looking for the points of inflection on a first derivative graph are going to be the minimum and maximum points. On your G prime graph. So when x equals 0, if you imagine the derivative of this graph, it's positive, it's 0, and then it changes to negative. So that's the second derivative changing sign, and it equals 0 at the top. So x equals 0 is going to be the location of a point of inflection. And then we have a minimum point right here where x equals 4. The derivative changes from negative to positive, or the second derivative technically changes from negative to positive at that place. So x equals 0 and x equals 4 are going to be the places where g has inflection points, where the second derivative changes sign. And in part E, the equation of the tangent line to G at x equals -2. Whenever we write the equation of the tangent line, we need to evaluate that function at that value. That gives you the point. And then the slope of the tangent line is going to be the derivative evaluated at -2. So for the point g of -2, I'm using this integral, the integral from 0 to -2 of f of t dt. Now, since we're going from 0 to -2 and we're integrating backwards, we make this area negative. Another way to think of it is this property, the integral from a to b of f of x dx is equal to the negative integral from b to a of f of x dx. So if you switch your limits of integration, you would put a negative out front. So I could also write this as negative integral from -2 to 0 of f of t dt, and then I'm integrating from left to right. This section right here, just like before, that's pi. This is 2, but it's going to be negative pi plus 2, or negative pi minus 2. Now for the slope of the tangent line, g prime of -2, since we are looking at a g prime graph, that's going to be the y-coordinate of the graph when x equals -2, and that y-coordinate is 1. So now to write the equation of the tangent line using point slope form, y minus y1 is when I plugged -2 into g, so that's negative pi minus 2. M is 1, the slope of the tangent line, and then x minus -2 is going to be plus 2. And that would be the equation of the tangent line. I could simplify it, but I don't need to. The next part of this lesson is kind of an algebraic application of the fundamental theorem of calculus. But just to reiterate, the fundamental theorem of calculus says when we take the derivative of an integral, those two operations cancel each other out. And we just take the variable and plug it in. But in this case, we're also going to do some examples where up here we have not just an x, but maybe some other function like x squared or 2x plus 3 or something a little more involved. And in that case, it's going to involve the chain rule because you get a composite function. When you plug g of x in for t, you get f of g of x, but then we have to multiply by g prime of x because of the chain rule. Now in both those examples, we ignored this a down here. We ignore the constant because the derivative of a constant is 0. Another thing you might see is variables both at the top and the bottom. And if that happens, what you're going to do is, again, the derivative cancels the integral, so those go away. You plug the upper function in, and you have to consider the chain rule. And then you subtract, and you plug the lower function in, and consider the chain rule for that part as well. So let's do some examples. Okay, in this first one, the derivative cancels the integral, and we just plug x in for t. And we get the square root of x squared plus 1. Notice the function, our answer, is exactly the integrand, except t becomes x. And we ignore the constant at the bottom because the derivative of a constant is 0. In the next one, it says g of x equals the integral from 2 to x of 3t squared plus 2t. Find g prime of x. So different notation this time, but same idea. We're taking the derivative. So differentiating this integral, we cancel out the integral and plug x in for t, and we need to plug it in both places. So we get 3x squared plus 2x. Okay, on to number 4. Find the derivative of f of x equals the integral from pi over 2 to x squared of cosine t dt. Pi over 2, the lower limit of integration, is a constant still, so derivative of a constant is 0, so I'm not going to do anything with that pi over 2. I'm going to plug x squared in for t, and the derivative cancels the integral. So we get f prime of x equals cosine of x squared, but we do have a chain rule step because x squared has its own derivative. It's the inner function of the composite function, so I need to multiply it by the derivative of x squared, the derivative of that inside function that I plugged in, and that's our chain rule step. Now in this next example, the constant is at the top of the integral and the variable is at the bottom. I don't like it situated that way, so I'm going to apply the property where I switch my limits of integration and throw a negative out front. So I'm going to rewrite this as h of x equals negative integral from -3 to x. So I switched those limits of integration and put a negative out front. Now the variable's at the top. 3t squared plus sine t dt. And now when I take the derivative, h prime of x, the differentiation cancels the integral, but I keep that negative out front. I'm going to put a set of parentheses, and I plug the x in for the t in both places, and I get 3x squared plus sine of x. And that negative is out front of the set of parentheses. You could also distribute it. Okay, and one last example. In this case, we have variable expressions both at the top and at the bottom. And so what we're going to do is plug in the upper limit of integration for both t's, and then we're going to subtract and plug in the lower limit of integration for both t's. And it will involve the chain rule. Let me clean this up and zoom in a little bit. So here's how it goes. R prime of x equals, I take x squared and plug it in both places. And I'm going to put a set of parentheses around this. 2x squared, which is then squared because I plugged that into t squared, minus x squared plus 4. Now x squared has its own derivative, which is 2x, so I need to multiply by 2x because of the chain rule. And then what I do is I subtract, and I take this lower expression and plug it in to the function inside the integral. So I'm going to put it in parentheses again. 2 times 3x squared minus 3x plus 4. And now this one also has its own derivative. The derivative of 3x is 3, so I'm going to multiply by 3 because of the chain rule. So those parts in red are the chain rule for each part. But we plugged in the upper function, applied the chain rule, subtract, plug in the lower function, apply the chain rule. And we could simplify this expression, but in the interest of keeping this video not too incredibly long, I'm going to stop there. This last example is a contextual example where we use the fundamental theorem in the context of rates of change. So this is a calculator AP style problem. It says the rate at which people enter an amusement park on a given day is modeled by the function E, defined by E of t. The rate at which people leave the same amusement park on the same day is modeled by the function L, defined by L of t. Both E of t and L of t are measured in people per hour. Units are going to be really important in contextual examples, by the way. And time t is measured in hours after midnight. These functions are valid for 9 is less than or equal to t is less than or equal to 23, the hours during which the park is open. At t equals 9, there are no people in the park. let h of t equal the integral from 9 to t of e of x minus L of x dx for t between 9 and 23. The value of h of 17 to the nearest whole number is 3,725. Find the value of h prime of 17 and explain the meaning of h of 17 and h prime of 17 in the context of the amusement park. Okay, so the big idea here is when we do the integral of a rate of change, we get an amount. So if e of t is the rate at which people enter the park, if I were to write an integral from 9 to t of e of, I'm going to change this to an x just because I need to use a different variable, e of x dx, that would represent the amount of people who have entered the park at time t. And if I wrote the integral from 9 to t of L of x dx, that would represent the amount of people who have left the park at time t. So again, when we integrate a rate, we get an amount. Our units for E of t and L of t are in people per hour. And the units for the integral from 9 to t of E of x dx are just going to be people. So we multiply by the units of the independent variable when we do an antiderivative. Remember, when we took derivatives, we divide by the units of the independent variable. So back to answering this question, they told us that h of 17 equals 3,725, and we are supposed to explain the meaning of that in the context of the amusement park. The meaning is, since h of x is the integral from 9 to t of e of x minus L of x, well, that's going to be the amount of people who have entered minus the amount of people who have left, which is going to be the amount of people in the park at time t equals, in this case, 17. Which of course is 5 p.m. And then we also need to find h prime of 17. H prime of t, if we take the derivative of this, we are going to cancel out the integral and plug t in for x. So h prime of t is going to be e of t minus L of t, which is the rate at which people enter minus the rate at which people leave. And so we get basically the rate of change of the amount of people in the park. And so h prime of 17 is going to be e of 17 minus L of 17. At this point, since this is a calculator problem, we would want to define our functions in the calculator, and I'll show you what that should look like. If you're using a TI Inspire, I recommend that you define your two functions. This was e of t, and this was L of t. And then we're basically just plugging 17 into each one and subtracting those values. You don't have to define the functions. Obviously, you could just plug 17 into E, plug 17 into L, and then subtract the values. And then I had to press Control Enter to get that decimal approximation rather than the exact answer. So h prime of 17 is negative 380.5 0.281, always round to, oh, actually it says to round to the nearest whole number, so I'm just going to ditch those. About negative 380, and the units are people per hour, or I could write that as people over hours. And what that means is it's the rate of change of the amount of people in the park at t equals 17 hours or 5 p.m.